The idea of quantum nature of light emerged in an attempt to explain photoelectric effect, blackbody radiation, thermionic emission, atomic spectra. So it is blackbody radiation. It's a trivial question. To explain blackbody radiation, that is, if this is a black body heated to high temperature, and if it becomes red hot, blue hot, yellow hot, then this starts emitting radiation. This we know. And the spectrum of blackbody radiation is continuous, means graph of intensity versus wavelength is this. If you observe, all wavelengths are present. Continuous spectrum means all wavelengths are present with different intensities. So to explain this continuous spectrum, quantum theory was used. Whenever a stream of electrons collide with a stream of photons, in this collision, which of the following is not conserved? Electrons colliding with photons or photons colliding with electrons. Okay. Which of the following is not conserved? Linear momentum, it is always conserved. Total energy, conserved. Number of photons, number of electrons. Which of the following is not conserved? Number of photons is not conserved. Students, underline terms like not, wrong term, not true, okay, false, because we often neglect this and try to go to the correct option. Now in this case, number of photons. Suppose this is a photon of energy 4 eV and this is an electron particle. After interaction, there could be emission of 2 photons from this electron. So one photon could be 1 eV and the other photon could be 3 eV. Thereby total energy is 4 eV. Suppose if the collision is like this, photon interacts with an electron and energy of first photon is 1 eV, energy of second is 2.5 eV, initial energy is 4 eV, okay, in my example. Then kinetic energy of electron is remaining 0.5 eV. See, sum of these three is equal to 4 eV. Why the photon number is not constant means the electron can have different energy levels. Suppose these are the energy levels of electron. If electron after absorbing 4 eV can go to this level, then it can come down to the ground state like this with the emission of a photon, 1 photon, or else the electron can come down like this, first, second. So in this type there can be emission of 2 photons. First photon corresponding to this energy difference, second photon corresponding to this energy difference. So there is emission of 2 photons, this and this. So photon numbers is not conserved, but linear momentum, total energy and number of electrons are conserved. Einstein's photoelectric equation, it is photoelectric. So common mistake is E equal to mc square. This is also from Einstein but not photoelectric. So E equal to work function plus kinetic energy. Second option. This is Einstein's mass energy equivalence relation. Mass energy equivalence relation. This you will learn in the chapter nuclei. Okay. E equal to mc square. Einstein's photoelectric equation may also be written as, so E equal to work function plus kinetic energy. This is maximum kinetic energy. Time being, let me write just Ke. This form is not here. and observe frequency. Energy of incident photon is h nu. Work function is h nu naught plus. Here kinetic energy is in terms of stopping potential. So E Vs. H nu equal to h nu naught plus EVS. Correct. Check this. H nu. This h nu should be on the left hand side. Not correct. In this, not correct. In this, not correct. So first option. Energy of a photon increases with the increase in. So energy of a photon is h nu. So energy increases with the increase in frequency. This is frequency. Photoelectric effect supports the concept that light waves are transverse. No. Light waves are longitudinal. No. This photoelectric effect doesn't support wave nature. That light waves are electromagnetic. This is also wave nature. Photon theory of light. Yes. Photon theory is nothing but quantum theory. Okay. Quantum theory. This beauty of quantum theory, H is used. Planck's constant is used. So this supports photon theory or quantum theory. Energy of a photon increases with decrease in. So energy is h nu equal to hc by lambda, because V equal to f lambda, isn't it? So in place of V, let me write C. Frequency nu lambda. So frequency is C by lambda. So nu is C by lambda. So energy increases with the decrease in wavelength. With the decrease in wavelength. Which of the following is Einstein's photoelectric effect equation? Observe. E equal to work function plus kinetic energy. Frequencies. Energy of incident photon is h nu. Energy of or work function is h nu naught plus kinetic energy is expressed in terms of velocity. So it is half m v square. Not correct. Not correct because of minus sign. Not correct. This is correct. Take minus h nu naught to the other side. Yes. The maximum kinetic energy of the photoelectrons depends only on kinetic energy of photoelectrons, incident angle, potential, pressure, frequency. So E equal to work function plus kinetic energy. For a given material, this is constant. For a given material or metal. Okay. So kinetic energy depends on energy of incident. Energy of incident means h nu, or energy of incident means hc by lambda. So kinetic energy is affected by energy, not there. Frequency, yes. If frequency is not there, then we have to go to wavelength. Students, try to depend on equations. Okay, to analyze, to get the answer, try to use equations. If the question is numerical type where values are involved, certainly you have to use equations. But questions like this where a concept is involved, in such questions also try to depend on equations. The work function of a metallic substance is 5 eV. The threshold frequency is approximately work function threshold frequency. So work function is h nu naught. But this work function is in eV. So eV to joule means multiplied by charge of electron. Okay. So threshold frequency is 5 by h. 5 is 5 1.6 10 power minus 19. Now this is in joule by Planck's constant 6.6 10 power minus 34. This is 8 10 power minus 19 by 6.6 10 power minus 34. Now simplify these two. 1 10 14 10 to the power of 14 15. 8 by 6.6. 8 by 6.6 is greater than 1. Greater than 1, it is 1.2 1.6, but we should get 10 to the power of 15. So this is, observe students, you are not simplifying fully, but you can guess the value of this. Okay, 8 by 6.6 means numerator is greater than denominator, but slightly greater means it should be greater than 1. Observe 4 options. These two are greater than 1. This is very much greater than 1, and this is also very much greater than 1. When you decide between these two, take care of 10 power 7, but here we should get 10 to the power of 15. Therefore 1.2 10 to the power of 15 Hertz. The magnitude of saturation photoelectric current depends upon, recall this graph. So this part is the saturation current. So it is a graph of photoelectric current versus anode potential. The magnitude of saturation photoelectric current. So magnitude of this current. If intensity of incident light is more, then this is how we get the graph. If intensity is less, then this. X-intercept gives stopping potential, whereas magnitude of saturation current depends on intensity of incident light. A radio station operates at a frequency of 10 megahertz with a power output of 500 kilowatt. Assume H equal to this. Rate of emission of quanta is. So they are giving power equal to energy by time, and total energy is number of photons into energy of each photon. Okay, students, N is number of photons, H nu is energy of each photon divided by time, and this N by T is nothing but rate of emission of quanta, nothing but photons. So N by T is P by H nu. P is power is 500 kilowatt, 500 kilo divided by H, 6.63 10 power minus 34. In multiple choice questions, 6.6 is enough. Frequency is 10 megahertz. 10 mega is 10 power 6 equal to, observe, numerator is 10 power 5, denominator is 10 power 6, 10 power 5, 10 power 6 is 10, 10, 10, 100, 10 power 2, 10 power minus 32. This goes to numerator, 10 power 32, 5 by 6.6. Numerator is less than denominator, so this ratio should be less than 1. Observe. So 0.8. So this should be 0.8 10 power 32. But in this 0.8 there is 10 power 30. Give 1 0 to this. 8 10 power 31. Yes. So this is rate of emission of quanta. Students, can you guess unit of this 8 10 power 31? It is number by time. So this should be per second. Per second doesn't mean that it is frequency. It is number of photons emitted per second. Okay. Energy of a photon is this. Its momentum is. So E equal to mc square. E is also equal to h nu. So mc equal to h nu by c. What is h nu? Energy. Energy is given 9 10 power minus 19. C is speed of light in vacuum 3 10 power 8. Mass into velocity. Mass into velocity is momentum. That is why I isolated mc from mc square. Okay. So 9 by 3 is 3. 10 power minus 19 by 8. This goes to numerator. Minus 27. So this is momentum. Since these two are in SI units, they should be in kg meter per second. So also check the SI unit. Okay. Sometimes in between CGS unit is used, like kg centimeter per second or gram meter per second or gram centimeter per second. That time we have to modify this suitably. Okay. Now this is 3 10 power minus 27. This is the common mistake. When students are simplifying this, they write this ratio as 10 power minus 11. 19, 8 minus 11. That option is also here, but this is wrong. So when you get numbers like this, you should always remember that, oh, we may go wrong here. We should be careful while dealing with this negative sign. So here in this case, it is minus 27. Light of wavelength is incident on a potassium surface. The stopping potential for the emitted electrons is, stopping potential is 0.42 volt. What is the maximum kinetic energy of photoelectrons? So stopping potential gives kinetic energy, which is 0.42 electron volt. This is in joule, but this option is already here. Kinetic energy electron volt, stopping potential volts. Light of frequency 10 to the power of 15 Hertz falls on a metal surface of work function 2.5 eV. The stopping potential of photoelectrons is light of frequency 10 to the power of 15 Hertz. So nu is 10 power 15, which gives energy. Energy is h nu. To find stopping potential, kinetic energy should be in eV. Okay. So here only let us divide this by charge of electron. So h is 6.6, 10 power minus 34. Frequency is 10 power 15 by charge of electron 1.6, 10 power minus 19. And this 16 forza. This one time, this approximately 4 times. Minus 19 goes to numerator, plus 19, 19, 15 is 34, plus 34. So this and this get cancels. So this is approximately 4 eV. This is energy. Einstein's photoelectric effect equation is E equal to work function plus maximum kinetic energy. Energy of incident is about 4. Work function is 2.5. Kinetic energy. Kinetic energy is 4 minus 2.5 is 1.5. Very close to that, 1.6. This implies that stopping potential is 1.5 or 1.6 electron volt. In this chapter, many cases, many times we come across 6.6 by 1.6. So this ratio is approximately 4.1. Okay, this is enough for this calculation. In an experiment of photoelectric effect, the stopping potential was measured to be V1 and V2 volts with incident light of wavelengths lambda and lambda by 2 respectively. The relation between V1 and V2 may be energy equal to Hc by lambda. New energy is Hc by lambda by 2, which is 2 Hc by lambda. See, this energy is twice this energy. So E2, E dash is 2 times E. Okay. Now, let me use induction method. Induction method means by giving values. So E equal to work function plus kinetic energy. Let work function be 1 eV. Energy of incident 2 eV. Then kinetic energy turns out to be 1. New energy is 2 times. Let this be increased to 4. Work function is same. Then this is 3. Observe, this is greater than 2 times this. So with respect to kinetic energy, we can get V2. With respect to this kinetic energy, we can get V1. So V2 is greater than twice V1. Let me give one more example. Let me give one more value. If energy of incident is 5, work function is 1, then kinetic energy is 4 unit. Suppose 5 is increased to 10 because twice. Okay. If this becomes 10, this is 1, remaining is 9. Again 9 is greater than twice this, greater than twice the initial value. So in these two examples, we get the same result, means this should be correct. Now let us solve this by regular method by using equations. E equal to work function plus kinetic energy. This kinetic energy has E times stopping potential plus work function. This is Hc by lambda because energy of incident radiation is given in terms of lambda. Now let me rearrange. EV equal to Hc by lambda minus 5, or V equal to Hc by, let me divide throughout by E. I get this minus 5 by E. Now with wavelength lambda, stopping potential is V1 Hc by E lambda minus 5 by E. With wavelength lambda by 2, V2 equal to Hc by E lambda by 2. This by 2 becomes 2 minus 5 by E. Now let me subtract one by the other. V2 minus V1 equal to this minus this. This minus this, here 2 times. This is 1 time. So it is simply Hc by E lambda. This minus this, 0. But what is Hc by E lambda? From this Hc by E lambda equal to V1, let me take this to this side, plus 5 by E. So in place of this, I can write V1 plus 5 by E equal to V2 minus V1. Observe carefully. V2 equal to minus V1 to the other side becomes plus V1. There is already V1. So 2 V1 plus 5 by E. Work function is positive, charge of electron is positive, therefore this is positive. So V2 is 2V1 plus some number, means V2 should be greater than to V1. So that is this relation. Plot of kinetic energy of emitted electrons versus frequency. So kinetic energy versus frequency is this. X-intercept gives threshold frequency, produce this. Y-intercept gives work function, and slope of this graph, slope of this curve gives Planck's constant, isn't it? We know all these three quantities. Straight line with a positive y-intercept. This is negative y-intercept. The curve is cutting the y-axis at the negative side. Straight line parallel to x-axis. No. Straight line passing through the origin. No. Straight line with a negative y-intercept. Yes. Straight line with a positive y-intercept means the curve should look like this. So this is positive y-intercept, whereas this is negative y-intercept. Plot of kinetic energy of emitted electrons versus applied potential. So potential does not affect the kinetic energy. Let me write E equal to observe, energy can be written in terms of frequency or wavelength. Work function h nu naught or hc by lambda naught. Threshold wavelength, wavelength of incident radiation. Threshold frequency, wavelength of incident frequency. Plus kinetic energy. Plus kinetic energy. So kinetic energy is affected by energy or frequency of incident radiation or wavelength of incident radiation or threshold wavelength, threshold frequency, and it doesn't depend on the applied potential. It doesn't depend on applied potential means it should be a constant term. Constant term is straight line parallel to x-axis. Straight line with positive y-intercept. Straight line parallel to x-axis. Straight line passing through the origin. Straight line with negative y-intercept. So this is the answer. Meaning independent of x quantity. Kinetic energy independent of the applied potential. Red, blue, green, violet color lights are one by one made incident on a photocathode. It is observed that only one color light produces photoelectrons. That light is. So energy equal to h nu or hc by lambda. Okay. Lambda for violet is less than lambda for extreme red. But lambda is inversely proportional to energy. So energy of violet is greater than energy of red. And all other energies are between violet and red. Here also all other wavelengths are between violet and red. It is observed that only one color produces photoelectrons, means that which is with highest energy. So that is violet. Violet. When a piece of metal is illuminated by a monochromatic light of wavelength lambda, stopping potential is 3 Vs. So wavelength stopping potential E equal to phi plus kinetic energy. This is hc by lambda phi plus charge times stopping potential. So this equation has lambda as well as stopping potential. Okay. So with lambda, hc by lambda, stopping potential is 3 times Vs. So E into 3 times Vs. When same surface means same work function. illuminated by light of wavelength 2 lambda, hc by 2 lambda. Stopping potential becomes Vs. So it is EVs. The value of threshold wavelength for photoelectric emission will be, threshold wavelength is with phi, because phi equal to h nu naught or hc by lambda naught. So threshold wavelength is here. Okay, so we should find phi first. These two are simultaneous equations. When you directly simplify, you will lose phi. This minus this, phi get cancels. But we need to retain phi, which can give lambda naught. Now I should retain this, means I don't want this. I don't want this means coefficient of this is 3. If I have 3 here, means multiply throughout by 3. This minus this or this minus this is 0. This minus this is 2 times 5. This minus this. Observe, 3 by 2 is 1.5. This is 1. 1.5 minus 1 is 0.5. So this is half hc by lambda. But what is phi? Phi is hc by lambda naught. This implies lambda naught equal to hc get cancels. Lambda naught is 2 to 4 lambda. So it is 4 lambda. 4 lambda. So with little practice, you can solve equations like this. Every time you don't have to repeat the equations with slight changes. Okay. So wherever we have to make corrections, wherever we have to make changes, in the existing equations only you try to make and then simplify.